we're finishing chapter 22, so we're talking about hypothesis tests. So what are the 4 steps to a hypothesis test? That's the second step. Right, so you state your hypotheses, then you check your conditions. Then what do? You do the math, you do the mechanics, and then what do? Make a conclusion. All right, so those steps are never going to change. For every hypothesis test we do all year long, those are the steps. Every single one. Okay, so first thing we need to talk about then is hypotheses. We're about 2 separate proportions. Now, in chapter 20, when you had a 1 proportion z-test, you were comparing that 1 proportion to what was happening in the population. So you had a p-hat and a p, right? In this case, most of the time they aren't going to give you p. They're just going to give you p-hat. They're going to use 2 samples. So you have 2 different groups, so you have 2 different samples. All right? So just keep that in mind. You're not going to have 4 different proportions like rolling around. You're just going to have 2. When you have a null hypothesis, you're always assuming that there's been no change, right? That's what we did in chapter 20. So in this case, we assume generally the same thing. We assume there's no difference in the proportions. We assume there's no difference in the groups. Or we assume the groups are the same. So there's 2 ways to write the null hypothesis. One is to write that the first proportion equals the other. Now, you're not actually going to have numbers in these. Okay, so if you're talking about proportion of men and women doing something, you'll have the proportion of men equals the proportion of women. You're not going to actually have a value associated with that. Okay? So that's one way to write it. The other way to write it, which makes it seem more like you're talking about the difference in proportions and it'll make more sense when you're doing the mechanics, is that you have 1 proportion minus the other equals 0. So the difference is 0. Both of those things mean the same thing. You can write it either way. I think it'll make more sense if you write it the second way just because it shows there's a difference and you're showing the difference is 0, and that'll come up with the mechanics. But that's just me. So your alternative hypothesis will be similar to what we did in chapter 20. You'll just change the equal sign to greater than, less than, not equal to. Do you want one group, do you want the difference to be positive because the one group is larger than the other? Do you want it to be negative, so it's less than 0? Do you want it to be not equal to, just showing a change? Similar idea. Questions about hypotheses? All right. The second step then is the conditions. I'm not going over those again. We added a condition in this chapter. What did we add? The groups. Yeah, you have to do the conditions pretty much twice, right, because there's different groups. But then you also have to have independent groups. All right. So if we're talking about men and women, we'll say that all the men are independent of each other and all the women are independent of each other, but also the men and women are independent of each other. Okay. So everyone knows those conditions. We have independence, randomization, 10%, success, failure. Those all are still at play. Questions about the conditions? All right, then let's talk about the math for a second. In chapter 20, when you're doing the mechanics, what were the steps to finding, or what were the steps of the mechanics in chapter 20? See the standard deviation, which was this, right? And then what do we do? After the standard deviation, what do we find? Z, which was p hat minus p over the standard deviation. Remember, it says on the formula sheet, test statistic equals statistic minus parameter over the standard deviation of the statistic. We're going to use that today to make sense of what we're talking about. But so we found Z, and then once we found Z, what do we do? Right, you have to find a p-value based on that z-score. So you're finding the probability that Z was less than, greater than some value using normal CDF. right? The mechanics here are generally the same. We're going to find the standard deviation first. This time, though, like I said, you're not going to have population proportion. So we're really finding the standard error because we're going to be doing it based on an estimate. Now, here's what we have to say about that. The standard error is a little bit different here. We have an equation for standard deviation that we can use for standard error when there's two proportions. We did it with confidence intervals on Monday, so that wasn't a big deal. But here's the difference. In our hypothesis test for two proportions, what are you assuming in the null hypothesis? They're the same, or there's no difference between the two, right? So if you're assuming they're the same and there's no difference between the two, then you shouldn't be using two different proportions in your standard error, because that would indicate that they're different. So because of that, for the standard error, don't write this down. We're just going to talk about it. We need to pool the values. So this is what we would normally write for our confidence interval, but again, that doesn't show that that shows we have two separate entities, and we're trying to assume that they're the same all the way through. So to pool the values, we're going to get one single proportion for the overall test by taking the number of successes in group 1 and adding it to the number of successes in group 2 and dividing by the total number of people in our sample. All right, so we're going to get one p-hat value. Because again, we're assuming they're the same, so we have to represent it with something that shows that they're the same. So if one p-hat value, so one q-hat value. You don't do that for an interval because we're not trying to assume anything's the same for an interval, but you do that for a hypothesis test. So keep that in mind. So here's the steps here again. Two proportion z-test. You have your hypotheses, you check your conditions. You're going to write a sentence about it and say you're doing a two proportion z-test because now this is the fourth different thing you know how to do. One proportion z intervals and tests, and now two proportion z intervals and tests. So you just say what you're doing. You find your p-hat pooled so you can find your standard error, which is just that equation we used before, p-hat q-hat over n and plus p-hat q-hat over n, and we take the square root. But we're going to use that pooled value. And then to find z, we talked about, it's the statistic minus the parameter over the standard deviation. So our statistic, we're talking about a difference in proportions. So our statistic is the difference in the two proportions. Again, that's the one time you actually use those two proportions in the test individually. Minus 0. Why is this a 0? Why is our parameter 0? What did we say the difference was in the null hypothesis? 0, right? So just like in chapter 20, we put what happened in the null hypothesis. Well, in the null hypothesis, we said there was no difference. So we say minus 0. And we divide by the standard error. Once we have z, we can find a p-value. Once we have a p-value, we can make a conclusion. Everyone have a general idea about what's happening. We're going to do an example all the way through. But questions about why things are what they are at any point. It's just 1 minus p-hat pooled. But yes. Any other questions before I actually do an example? Okay. A Vermont study published December 2001 by the American Academy of Pediatrics examined parental influence on teenagers' decisions to smoke. A group of students who had never worked were questioned about their parents' attitudes towards smoking. These students were questioned again 2 years later to see if they had started smoking. The researchers found that among the 284 students who indicated that their parents disapproved of kids smoking, 54 had become established smokers. Among the 41 students who initially said their parents were lenient about smoking, 11 became smokers. Do these data provide strong evidence that parental attitude influences teenagers' decisions about smoking? All right, before we do anything, I need to figure out what the two P hats are just so I have them. So I'm going to have P hat. I've got two groups, right? I've got a group of students who have parents that disapproved of smoking, and I have a group of students who have parents that are lenient about smoking, so I'm going to denote that with disapproving parents and lenient parents. You have to somehow indicate which P hat you're talking about. So the disapproving parents, we had 54 that became smokers out of 284. And for lenient parents, we had 11 become smokers out of 41. And because I don't want to do all the math in the calculator again, that is 19% and 26%. So that's the percentages we're dealing with in this question. So if we're going to go through this question, do all what it asks. A is a good review question. What kind of design did the researchers use? What kind of design was used to get this information? Has to be a survey, observational study, or an experiment. Observational study. Why is it an observational study? Over time. And so is it retrospective or prospective? Prospective. You picked a group of kids and then you went and followed them for 2 years into the future. It'd be retrospective if you went back and looked at some records about their smoking habit. All right. On B, it says write appropriate hypotheses. Again, I'm going to always write them as a difference. And then I'm also probably going to write it so the difference is greater than 0 because that makes things positive and makes my life happy. But you can do it however you want. So for my null hypothesis, I'm going to say that the proportion of lenient parents minus the proportion of disapproving parents groups was equal to 0. You don't have to do it in that order. You can do a different order. It's going to change what your alternative hypothesis is. So that's fine. It just asks if these data provide strong evidence that parental attitude influences teenagers' decisions about smoking. You can interpret that as not equal to, but there's such a wide gap in the percentages that I'm just thinking we're doing a one-tailed test here. So do you think my alternative should have greater than or less than? Greater than. 0.26 minus 0.19 would be greater than 0. Right? That's what we're basing it on. Questions? Oh, and these should not be p hats. That's just me not paying attention. Why should those not be p hats? We're always just talking about population proportions in our hypotheses, right? Not what's happening in the sample. All right. Part C. Are the assumptions and conditions necessary for inference satisfied? I am not going to write all these down, but we are going to talk about them. So what's a condition we should check? Randomization. Does it say that they were using random samples? No. So we need to say the 284 students with disapproving parents are a good representation of students who have parents that are disapproving of smoking. And the 41 students who have parents that were lenient about smoking are a good representation of students who have parents that are lenient about smoking. Questions about that? What's another condition? 10%. Is 284 students less than 10% of all students who have parents that disapprove of smoking? I would think so. And 41 students is less than 10% of all students who have parents that are lenient about smoking. What's another condition? Success failure. Now, some of you guys are doing too much work with success failure. If you're given a percentage in the question, then yes, you have to do n times p and n times q to see successes and failures. In this case, we are given counts, not percentages. So you can still do the percentages thing. That's totally fine. But if you do, for example, disapproving parent group, this one right here, if you did 0.19 times 284, you get 54. So I know there's 54 successes, and then 284 minus 54 is 230, and so there's 230 failures. 54 and 230 are both greater than 10. Same thing for lenient. 11 is greater than 10, and 41 minus 11 would be what's left over, and that would be 30, and 30 is greater than 10. It's not wrong to do the percentage times the sample size, but if they give it to you as counts to begin with, save yourself some time. Okay? So that's almost all the conditions. What else we got? Independence. So we need to say 284 students are the 284 students with parents that disapprove of smoking are all independent of each other. The 41 students who have parents that are lenient about smoking are all independent of each other. And then the students with parents that disapprove of smoking and the students with the parents that are lenient about smoking are also independent of each other. Right? Independence within the group, independence of the groups. Questions about any of the conditions? All right. Then we need to write a sentence. Because the conditions are met, we can use a normal model for the sampling distribution for the difference in proportions. And we can use a 2-proportion z-test. We're doing a test on an interval, so make sure you call it a test. All right. Part D says test the hypothesis and state your conclusion. So we're actually going to do the work and do the mechanics in Part D. First thing we need to do, before we try to find the standard error or anything, is we need to find out what p-hat pooled is. Because we need to pool our information, because again, we're assuming that there's no difference in the groups. So to find p-hat pooled, we have 54 plus 11 over 284 plus 41. Questions about where those numbers came from. Number of successes plus the number of successes over sample size plus the sample size. That's 65 out of 325, and so that gives us a p-hat pool to 0.2. Questions about that? All right, then we're going to find, I'm going to write everything all together. So I'm going to find the standard error and z and stuff all in the same step, because I'm going to do most of it in my calculator anyway. And so I don't have to rewrite it all 15 times. So z is the difference in your proportions. So 0.26 minus 0.19 is the difference in our two proportions in our sample. Minus the difference in proportions for the null hypothesis. We're assuming there's no difference, so minus 0. Over the standard error, so we have the square root of 0.2 times 0.8 over 284 plus 0.2 times 0.8 over 41. Any questions about that? This ends up being 0.067. This difference is 0.07. So if you go back and look at it later, make sure that you get those numbers. All right, so if we do the math, 0.07 minus 0 is 0.07, and 0.07 divided by 0.067 ends up being 1.045. So that is z. So what do I do with the z? P-value. So how do I find the p-value? Right. So again, writing normal CDF on your paper is useless and worthless. You can do it all you want, but no one's going to look at it. So if you draw a really quick picture, put 0 in the middle, give 1 standard deviation, negative 1 standard deviation, so 1.045 is like right here. Am I looking for the area above or below that, and why? Above because, right, the hypothesis said greater than. If it said less than, you would be looking for below, even though it's a larger area. It's not just the tail that you feel like. It's whatever it says in the hypothesis. So the correct notation for this is the probability that Z is greater than 1.045. That's what we're looking at. In your calculator, yes, you're going to do normal CDF. You're going to go from 1.045 to infinity. And we're going to use the mean and standard deviation as 1. And our p-value ends up being 0.148. Thank you for taking my word for it today. I don't want to type it all on my calculator over and over again. Excellent. So once I have p-value, what do I have to do? State a conclusion. Your conclusion has 3 pieces. So what is the first thing we need to say? Yeah, so in this case, what are we going to say about p-value? P-value is large. Now again, eventually you're going to start giving alpha levels to you. So if it had said alpha equals 0.05, you want to directly relate that to the alpha level. You want to say the p-value of 0.148 is greater than the alpha level of 0.05. You don't have that right now, so you can just say it's high or it's large. Okay? Because it's large, what do? We fail to reject the null hypothesis. You just don't really fail to reject. You have to say what you're failing to reject. You're failing to reject the null hypothesis. Because we're failing to reject the null hypothesis, then what are we saying in context? I would just restate the question, right? We failed to reject the null hypothesis, so there is no evidence that parental attitude influences teenagers' decisions about smoking. Right? Yeah? Questions about the conclusion? Okay. Then part E says, what does the p-value mean in context? Which is not what it's asking for in the conclusion. What does this 0.148 mean? Yeah. So 14.8% chance that we would get similar sample results as we got in this question, given the null hypothesis was true. Or assuming the null hypothesis was true. That means it's not unusual. That's all we failed to reject. All right. Questions? That's really not in context. You have to write that in context about smoking somehow, but we get the gist. Questions about part E? All right, part F. If that conclusion is actually wrong, so we failed to reject, so that's incorrect. Which type of error did you commit? Type 2. In type 2, the null hypothesis is false, but you failed to reject it. So if you fail to reject, you're committing a type 2 error. If you said it was wrong. Type 1 is when the null hypothesis is true, but you reject it. So if you made a rejection, they say that's wrong. It's type 1 error. Questions about that? I can do another one if you want me to. That's up to you. Those are the, whatever you have in your hypotheses. I did lenient parents minus disapproving parents. Whichever one you decide. I did lenient parents minus disapproving parents, so I had to do lenient minus disapproving. Yes. Right. So if you had done this a different way, it's fine. You could do in the very beginning, P of disapproving parents minus P of lenient parents equals 0. You would change the alternative to less than 0. In your Z, you would do 0.19 minus 0.26 because you did disapproving minus lenient in your hypotheses. And then you would get a negative value, and you would have less than, so you'd do negative infinity to that value. It's symmetric, though. It would be negative 1.045. So you'd still get the same exact p-value. I just like things to be positive. Other questions?